that have been kind of discovered the last few years that are in the field of symplectic and contact geometry, and specifically about kind of reductions of this geometry to kind of topological objects. So I'll say more and more about what this means. So just to start with, so what's symplectic geometry? What's the kind of field we're working in? So it's some kind of geometry, and it's related to Hamiltonian dynamics. It's kind of the original starting point for it. And since then, it's gotten a lot more connections to low-dimensional topology and geometric topology in general, as well as algebraic geometry and especially, I guess, like more contemporary physics, string theory, and mirror symmetry. So the technical definition is a closed, non-degenerate two-form, though I think if you've never seen that before, probably it's not so useful. The relations to complex geometry is you can think of it as like the imaginary part of a Hermitian form. So this is kind of a connection with Kähler geometry. And then the particular sort of class that I'm interested in myself, which is kind of a very large class, is those of Stein manifolds, or so just holomorphic submanifolds of Cn, where you just restrict the natural structure. And what's kind of especially essential for symplectic manifolds is that they have no moduli. So if you deform them, it kind of doesn't change them at all, any deformations induced by an isotopy. And because of that, you can prove, for instance, they have no local invariance, but just in general, you can kind of like stretch and squeeze and cut and paste them, and it kind of gives the field a more topological flavor, I guess. Okay, and now, so the other geometry that I want to talk about today is contact geometry. And it's a very similar sort of geometry, but it lives in odd dimensions rather than even dimensions. So by definition, it's a maximally non-integrable hyperplane field, which again is probably not super useful if you've never seen it before. I think a good intuition is that if you have one of these Stein manifolds and you look at how it is intersecting a sort of large radius sphere, then that has a contact structure which is just induced by all the complex tangencies to that manifold. And so, like symplectic structures, they're kind of topological objects. We can kind of play with them and sort of cut and paste topology sort of tools. And this contact structure determines and is determined by this kind of symplectic structure at infinity, as kind of described here. So I think one motivation for thinking about contact structures, if you take from the beginning that symplectic structures are worth thinking about, is that, well, I want to understand symplectic structures, and one way I want to do that is chop them into many pieces along like hypersurfaces, and then maybe I can study small pieces and then glue them together. So if I want to know how to do that, well, the kind of natural framework is contact geometry, since that's kind of giving me that structure near a hypersurface, at least for particular hypersurfaces. So the kind of standard picture is this one here. And so you see that there's this kind of hyperplane field which has this property that there's no surfaces tangent to it, at least in this dimension, and higher dimensions, it's kind of similar non-integrability. And this is a useful model because, as I said, there's no local invariance. So if I have any contact structure on any smooth manifold, well, I'm just taking these like in a whole bunch of different places and gluing them together, right? Like I can kind of build an atlas out of these models. Okay, so the main kind of question now I want to focus on, which you can do in many other fields, but it's kind of particularly useful in contact and symplectic geometry, is to kind of really precise the well, distinction between geometry and topology. So what does this kind of mean? So if I have any geometric question, there's always a corresponding weaker topological question. And there's some sort of process for always like figuring out what this weaker topological question is. So I'm going to use the word formal for these kind of weaker, purely topological structures. So the simplest kind of example of this is if I want to figure out what's a immersion, well, an immersion is just a map so that the derivative, is full rank everywhere. The corresponding formal version is, well, I don't know if it's the differential of a map, but I should at least have a bundle monomorphism, right? And that kind of removes all of the derivatives from the question, right? It's kind of purely now just algebraic topology. So in our case, a formal symplectic structure turns out is exactly the same as just a complex structure on the tangent bundle. And a formal contact structure is similar, but just a stabilized complex structure, which sort of makes sense, at least in this description I gave of sort of like hypersurfaces and Stein manifolds. And just to kind of emphasize that these are kind of like legitimately algebraic topology things, both of these structures, formal symplectic or formal contact, is just kind of lifts of the classifying map of the tangent bundle to the kind of complex groups. So, as I say, kind of in any field of geometry, you can always set up these corresponding formal questions as sort of first necessary hypothesis. But symplectic and contact geometry are especially kind of fruitful places where a lot of times this is sort of close enough, the geometry and the topology, that it's especially fruitful to kind of think in these terms, I would say. Okay, so the first sort of thing I'll talk about is the existence question of contact structures. So, of course, the very first question you could ask about contact structures is, well, I have a smooth manifold. Does it have a contact structure or not? And that's kind of, well, yeah, so it would be a good thing to know. So based on this discussion of formal things, kind of slightly better question would be, okay, I have a I have a smooth manifold and it has a formal contact structure. And can I find an actual contact structure which is realizing this kind of formal question? So first of all, it's certainly like a necessary hypothesis, right? If there's no formal contact structure, there certainly can't be a genuine one. But it's also a richer question, right? Because I'm asking not just is there a contact structure, but kind of in every possible sort of topological class of contact structures. Okay. Now, this has a history to it. So we've known the answer in 3 dimensions for sort of a long time. This is what's called the Lutz-Martinet theorem. And there's many different proofs of this by now. Essentially kind of, well, yeah, you can prove this using surgery descriptions of 3 manifolds or open book decompositions or kind of directly from triangulations. And in some sense, this is sort of, well, more classical, I suppose. Now, more recently, there's a couple of proofs by Casals, Pancioli, and Presas, and also independently by Etnayer, which proved existence of contact structures in the 5-dimensional case. And I won't talk so much about this, but maybe we'll say a little bit. Notice there's quite a sort of gap between these in terms of years. So, and then also in the last kind of few years, it was proven that in fact in all dimensions, every formal contact structure is realized by a genuine contact structure. So just a couple notes kind of on the history. So first of all, I wrote 2005 for both of these. That's not really true, though. I mean, those are the publishing dates, but they sort of precede our work by a couple years, anyway. Their work came out in like 2012, whereas ours was like 2014. The proofs are also substantially different, even kind of in the five-dimensional case. In the five-dimensional case, both the Casals-Pancioli process and the Ettmeyer proof sort of rely on kind of finding some sort of fibration for the five manifold, and then using classification results for three manifolds in order to complete the construction. Whereas ours, kind of an important feature, I would say, is that it's not inductive kind of on dimension, and I'd say that's in some sense kind of what made us able to kind of go further, I suppose. Okay, so now I'll give a very vague sketch of the proof now. So the first thing to understand is that building a contact structure on some subset is an easy thing to do. So kind of the first step to do is I can just triangulate the manifold, and then on a codimension 1 subset, it's easy to do, basically because like the contact structure just, in order to be a contact structure, sort of needs to twist enough as a hyperplane field. And if you have some sort of transverse directions to do that, well, you just make it like twist a whole lot in those transverse directions. Of course, you know, this takes up pages and pages of writing, but I think intuitively, this is an easy thing to do. So that reduces the entire question of, you know, all contact structures on all manifolds if I want to prove existence. I just need to figure out how to prove the extension problem from, you know, the neighborhood of the boundary of the ball to the interior of the ball. All right, so put a pin in that idea. Now, if I have any contact isotopy through, of just say the standard disk, so meaning just an isotopy through contactomorphisms. So contact geometry, like symplectic geometry, is a sort of geometry of Hamiltonian dynamics. And what that means is that any symmetry is given by an energy functional, and so the kind of any symmetry is sort of the dynamical flow of that energy function. One way to state this is the sort of Lie algebra of the contactomorphism group is just the space of C infinity functions. And furthermore, if kind of just coming from basic theory of contact manifolds, there's two important points. So first, if I have any contact isotopy, I can take the suspension of this, so kind of like take this isotopy and then use the time one map to glue my contact thing back to itself. And that actually gives me a germ of a contact structure near the sphere, kind of one dimension bigger. And furthermore, if this energy, which is generating the flow, is positive, it's kind of just immediate that this contact structure extends to the interior of the ball. This is sort of something that just follows by the definition of this suspension, I guess. Okay, so what have we done so far? So first of all, we just need to figure out how to extend contact structures from the boundary of the ball to the interior of the ball. And furthermore, I claim that, in fact, these suspension type are sort of general enough that those are the only ones that matter. So what I need to understand then is, well, how does this, you know, there's something special about this Lie group, which is that since its Lie algebra is C infinity functions, it has this well-defined positive cone, and I want to understand how that relates to the kind of Lie group structure, and because things which are positive always extend. And now there's one more sort of ingredient, which is what kind of genuinely makes this topology, I would say, which is that if I take one copy of the contact ball and another copy, and I just stick them together, that's still contactomorphic to a contact ball. And so by doing this, this gives me sort of, if I have a contactomorphism of this ball and a contactomorphism of this ball, then I can stick them together and I get a contactomorphism of the stuck together ball, which is the same ball once I choose a contactomorphism. And so by doing this, I get this sort of strange monoid structure on this Lie group, which I have no idea how to kind of think of it in terms of like Lie theory. It's kind of very strongly a kind of topological operation, I would say. So then ultimately what our proof does is we show that basically you can't make all these things compatible. So if I want to understand how does, why does anything extend, so like a non-extendability is some sort of causality, right? It's some sort of well-defined notion of positivity. And because there's no, as it turns out, as we sort of figure out by kind of studying some specific properties of this dynamics, that there's no causality. So there's kind of points inside of this Lie group from which you can get to every other point in kind of a positive direction, and even like get to the 2 copies of yourself from 1 copy. And using this, you can sort of destroy this ordering, and then this gives you some sort of extension. Now, of course, that's all very vague and naturally omits all the kind of interesting meat of the proof, but this is sort of the general takeaway, I think, is that this extension problem is related to this question of how positive energy affects the symmetry group, kind of 1 dimension down. It's also maybe worth saying, I would say philosophically, the reason the 3-dimensional case is so much easier and kind of, predates this like by 50 years, is that the contactomorphism group, so the 3-dimensional case is when n equals 2, right? And so if n is 2, I'm looking at the contactomorphism group of the interval, which is just the diffeomorphism group of the interval. So we understand this kind of significantly more, I guess. Okay, so now given this, what else can we sort of do with these techniques? So because contact structures have no moduli, that means that uniqueness of a contact structure is the same thing as parametric existence, right? Like, in order to prove that a contact structure is unique, I just need to find a way to interpolate between those contact structures via contact structures. So this is kind of a nice property of these sort of more topological geometries. And because we have this sort of proof of existence, if this proof was sort of canonical enough that it actually would work smoothly in families, then this would also give a proof of uniqueness. Now, this doesn't work. And in fact, long before we even did any of our work, we sort of knew that this couldn't work because contact structures don't have a uniqueness. So there are many contact structures which are distinct, but are formally equivalent. However, if, don't let that discourage you. Like, just because it's false doesn't mean you shouldn't try and prove it. And you kind of follow the proof enough and you see, okay, well, where exactly are we making non-canonical choices? What can I add any additional hypotheses in order to make these choices canonical? And we can get some sort of partial classification. And this is the kind of theory of overtwistedness. So here now we get the stronger result that says that every formal contact structure, not only is it realized by a contact structure, but it's realized by a unique overtwisted contact structure. So I haven't said what overtwistedness is, but it's some kind of specific subclass. So this kind of generalizes earlier work of Ellie Ashberg, where this has kind of been a significant sort of, I guess, staple in the three-dimensional theory for quite a long time now. Now, this theorem, as I stated it, is kind of has no content to it, because if you want to prove uniqueness among some sort of subclass, well, that doesn't take any proof. You just choose some. So there's, this is only going to be useful if I have interesting properties for what overtwistedness is, right? So there's work that I did with Casals and Presas, which relates high-dimensional overtwistedness with many other the kind of natural geometric structures in high-dimensional contact geometry, surgery descriptions, and Lagrangian submanifolds, open book decompositions, many other sort of related things. I don't really want to talk so much about this, but just suffice to say that it's kind of compatible with many other pictures we have. But I'd say the most important property of what overtwistedness is it's a sort of semi-local property. Now, of course, it's not local, like contact structures locally have no information. But what I mean is that overtwistedness is defined by containment of some kind of model. So if you contain sort of some subset which is overtwisted, then you're overtwisted. Now, what this actual model is sort of a complicated question, and also is connects to ongoing work. But in fact, just this semi-locality plus the statement of the classification, that actually uniquely determines which contact structures are overtwisted. It's sort of a universal property, if you want. So I think a great example of this, not only of overtwistedness, but kind of high-dimensional contact geometry in general, and what the kind of state of things is just the study of what are the contact structures on S5. So let me just get the set a name. So I'm going to call capital theta the set of all the contact structures on S5 up to diffeomorphism. And now there's a notion of connect sum of contact structures. So that gives a structure of a monoid on theta here. If I have two contact structures on S5, I can just connect sum them together, get another contact structure on S5. So we don't know very much. We know that it has an identity element, just kind of the standard sphere. We know that it's quite large. So I mean, it's definitely going to be countable just because it's a compact manifold and we have these sort of, it's discrete. But it's not even finitely generated. In fact, there are submonoids which have surjective homomorphisms onto Q. So this is due to Quan and Van Coort. And the fact that it's sort of quite large is originally due to Ustilowski. So this is sort of this huge thing. So what overtwistedness does for us is it gives us a zero element in here. So it's some sort of geometry which, even though the set of all contact structures on S5 is very rich. There's very many of them, not even finitely generated. But it's this geometry which destroys all other geometries. So, I may have this contact structure on one sphere, which is sort of all kinds of complicated and, classifying it as maybe like an extremely hard problem. But I have this other one which just, you connect sum it on, and it destroys all the interesting geometry on the other side. So yeah, that's sort of, I think, a strange sort of property that I haven't seen so much in many other fields of geometry. So I think that's kind of an interesting sort of behavior. So things we don't know, which I think are very important questions, is whether there are any units or whether there are any zero divisors. This question of units is equivalent to what I would call as kind of a contact Schoenflies conjecture, I guess, since we don't know what it is. And zero divisors, so this is asking if I can build the overtwisted sphere out of non-overtwisted things. Also, I think it's a very important question. Okay, so that's sort of existence of contact structures and overtwistedness and these sort of topics, which well, I think is kind of one neat thing about contact structures to happen recently. Now I want to move on to a new direction, which is submanifolds inside of contact in symplectic manifolds. So there's kind of two, I would say, most important submanifolds inside of contact in symplectic geometry. These are the Lagrangians and the Lagrangians. Inside of symplectic manifolds, Lagrangians are maximal dimensional submanifolds where the symplectic form vanishes. Equivalently, you can think of this as submanifolds, if I'm in this sort of Kähler case, where the orthogonal complement of the manifold is the same as multiplying by I. So locally, they look like kind of Rn inside of Cn, kind of in Hermitian coordinates, I guess, except I'm forgetting the complex structure. And now the kind of corresponding contact concept is Legendrian manifolds. And those are maximal dimensional submanifolds which are tangent to the contact structure. And just as contact and symplectic manifolds relate in terms of thinking of contact manifolds as kind of hypersurfaces in symplectic manifolds, Legendrians and Lagrangians correspond in this way. So if I have a Legendrian in a contact manifold, which is, or if I have a submanifold in a contact manifold, which is kind of a hypersurface in a symplectic manifold, then being Legendrian is if and only if the sort of small cylinder is a Lagrangian. So, yet again, we can ask similar questions, just as before, comparing the geometric questions to topological questions. So there's such a thing as formal Lagrangians and formal Legendrians. I won't formally define them here, but roughly they're kind of smooth submanifolds which have the right framing. And this is one place that's kind of very classical that we know that the topology and the geometry don't agree. So one sort of implication of Gromov's non-existence theorem for exact Lagrangians tells us that there's no Lagrangian S3 inside of C3, but there are formal Lagrangian S3s. Now, if I'm in high dimensions, it turns out that for Legendrians, there is an existence result, which says that anytime I have a formal Legendrian, it is realized by an actual genuine Legendrian. So this is false in 3 dimensions. This is kind of the really the first rigidity result anywhere in contact or symplectic geometry. And also in high dimensions and as well as low dimensions, uniqueness never sort of holds of, Legendrian isotopy types within their kind of formal isotopy type. So the situation, though, is quite similar to the situation for contact structures, meaning that we have a complete existence result. We don't have a uniqueness result, but there is some subclass where there is a uniqueness result. And just as before, this uniqueness, is kind of only interesting so far as we understand what this class is, where it's unique. And I won't define this, but again, it's kind of the same sort of semi-local property that if I have kind of a Legendrian containing a loose Legendrian, then it itself is loose. So that's a bit esoteric, sort of as stated. So I want to talk about a few applications of this. And the first sort of applications I want to talk about is constructions of sort of exotic Lagrangians. So as I said, Legendrians we kind of think of as being like how cylindrical Lagrangians intersect contact hypersurfaces. And because of this kind of close relationship between these, we can use isotopies of Legendrians to build Lagrangians, just kind of like graphing the isotopy. So one kind of manifestation of this that we proved a few years back is if you have any closed 3-dimensional manifold, then after connect summing a single copy of S1 cross S2, you can find an Lagrangian embedding of this manifold into C3. Now, just for maybe a bit of context, it's been known for a long time that if you connect some sufficiently many copies of S2 cross S1, that this is always possible. The basic reason is that you can prove that any L always will immerse as a Lagrangian into C3. And then once it's immersed, you can just kind of take your double points and then do some sort of surgery operation. And every time you do a surgery, it's just adding, extra tubes, which are just copies of S1 cross S2. So the kind of content in this theorem is that you only ever need a single copy of this S1 cross S2. A kind of equivalent, or in fact stronger way that this could be reformulated is that there's an exact Lagrangian immersion which only has a single double point. Now I won't go through the proof of this, but it essentially follows from this kind of like semi-locality kind of property I was saying. So the point being that as long as you have just kind of a single self-intersection, that's kind of enough to get you into this class of loose Legendrians. And then once you're kind of there, then you have the freedom to kind of do anything you can imagine because you have this kind of complete uniqueness understanding of what can be done. So one thing to point out is that besides just like their existence, these are interesting Lagrangians in that from the perspective of floor theory, they have most points on the Lagrangian, sort of generic points on the Lagrangian, there won't be any pseudo-holomorphic disks passing through that point. These are actually the kind of first Lagrangians of this type that were discovered, I guess. And it's sort of maybe important because this makes it sort of essential that the Lagrangian floor homology, rather than being 0, as it sort of should be for all Lagrangians in C3 or Cn, that the Lagrangian floor homology is sort of undefined, and it's undefined in an essential way that it shouldn't be able to be defined, at least not with sort of constant coefficients, I guess. Okay. So a similar kind of application of this, which is one I sort of like a lot, is again sort of connected with immersed Lagrangians in Cn. And the statement, there's a slight typo in here, but so it's that if you have any Lagrangian in say, even dimensional space. And let's assume that I have just a single double point. So it follows kind of just immediately from the formal structure that the Euler characteristic has to be plus or minus 2. If it's positive 2, then the Lagrangian actually has to be diffeomorphic to the sphere. So this is sort of a rigidity result. It's kind of telling you that most things don't immerse. However, if you have any smooth manifold at all, satisfying some formal condition here, then it always immerses with a single double point. The typo is just that if n is 2, we don't actually know that it's diffeomorphic to S4 because you get into, you know, smooth Poincare. But besides this, this is true. And yeah, I kind of like this because it, I think it really exemplifies this kind of distinction between the geometry and the topology, in that just such a slight change between whether this self-intersection point is positive or negative completely kind of changes the character of the problem. So in the case where it's positive 2, so this is really the positive 2 cases due to Ekholm and Smith. The point is that in this case, you can kind of always show that the pseudo-holomorphic curve theory works well, and then you can build a parallelizable manifold bounding it, and well, then you kind of go through surgery theory to get the diffeomorphism type. And then the kind of converse to this is that if you're in this case where you have a negative self-intersection, then you can get into this regime where this kind of flexibility and kind of topological freedom sort of takes over. All right. So now there's just one more application I wanted to discuss of these loose Legendrians, and this is to Weinstein handle-body theory. So if I combine symplectic geometry and this sort of classical Morse theory, then this gives me a powerful way to understand symplectic manifolds similar to the way that we understand smooth manifolds via Morse theory. So I can kind of think of Stein manifolds, if I'm kind of understanding Stein manifolds up to symplectomorphism, as being built just by successively maybe starting with the ball, say, and then attaching handles you know, in some sort of finite tower. And the symplectic structure is actually determined by the kind of contact isotopy type of the spheres that I'm attaching to in the contact boundary. So it's kind of classical Morse theory, but enriched with all this geometry. So now, because these handles are attached along, well, Lagrangians in this sort of contact boundary, I can ask what does loose Lagrangians do for me here, and that gives a kind of corresponding theorem. So this is this kind of notion of Stein of flexibility, which is due to Chilibach and Eli Ashberg, and well, it's kind of a classification here of them, though again, it's kind of maybe things aren't really defined well enough to really kind of get any content out of this. Both kind of formal Stein has to be worked out a bit of what a formal Stein manifold is, and then also flexible is kind of a key word here that isn't defined, but kind of follows from loose things. So using this sort of thing, this gives us a tool to kind of classify certain cases of symplectic manifolds. So my favorite example of this is work that I did with Roger Cassels. And so there's a famous threefold hypersurface in C4 called the Russell cubic, or Corus-Russell cubic. And this was sort of originally studied as, it was an interesting example of a affine variety which is diffeomorphic to C3, but not algebraically isomorphic to C3. And so using this sort of flexibility theory, we're able to prove that, in fact, it's not only diffeomorphic, but symplectomorphic to C3. Still an open question, which I think is very interesting, is we don't know whether or not this manifold is biholomorphic to C3 or not. The sort of proof that it's algebraically exotic goes through, well, either kind of looking at all possible algebraic C-star actions, or kind of similar techniques. There's a couple different proofs of this, but biholomorphism is still open. And a kind of similar example of this is, if I look at these hypersurfaces, so this is just some sort of example of some kind of basic hypersurfaces. It's a sort of Milnor fiber of a non-isolated singularity, if you like. And so this family, for B, positive integer, they're all symplectomorphic to each other, except for the case where B equals 1, in which case, of course, this is just the affine quadric. And I think there is sort of, you would never come across this, you would never suspect that this is true without this sort of flexibility theory sort of guiding this. Right, so I have just one kind of final picture, which is the proof we gave showing that the Corus-Russell cubic is standard. I'm not going to actually kind of explain this picture in detail, but just to give a sort of flavor of I don't know, maybe how topological these sort of things are. So at the top is sort of like a basic kind of sort of Weinstein handle decomposition picture of the Russell cubic, and then we have some sort of basic cancellations. And then once we get to here, this is where we kind of explicitly see that things are flexible. And then, it's not at all clear that this is trivial, but since it's flexible, then this sort of theory starts taking over. And then it's just immediately the same thing as C3. So yes, I'll stop there. Thanks for listening.
Are there any questions? In your sketch of the proof of, perhaps I missed it, where did you use the existence of a formal contact structure to prove the existence of actual contact structure?
Yeah, great question. Yeah. So I guess in a couple places. One that we need is first to even build it at all on the codimension 1 skeleton. And then secondly, we need to know that the formal structure, I have the sort of genuine structure on the boundary of the ball, which I'm sort of trying to extend to the interior. In order for this to work, I need to know that it extends as a formal structure to even kind of get this suspension type. So yeah, basically, like in order to get to this simpler version where everything is kind of local and just of this suspension type, it's needed for this.
I have a question. So there's a map from the space of overtwisted context structures to the space of formal context structures. Could you possibly show that that's a homotopy equivalence?
Yes, or nearly so. We show that the space of overtwisted structures with like a fixed overtwisted disk is homotopy equivalent to the space of formal structures with like a fixed point, say. So up to this kind of relative version, we have a complete homotopy equivalence. There's still an open question about what does the space of overtwisted disks in an overtwisted manifold look like, and that's very much open. Even in dimension 3, we know something, but very little about that question.
Any other questions?
Are there threefolds where the symplectic structure does detect algebraic exoticness?
Threefolds where... I mean, I suppose, well, yes. So I guess an example would be in this, these kind of X sub B's. These are all of them diffeomorphic, even for B equal 1. But the, for B at least 2, the fact that those are not algebraically equivalent to the quadric follows from the fact that they're not even symplectically equivalent to the quadric. There are also known examples which are diffeomorphic to C3, though, as well.
All right, well, we'll resume at 5 o'clock, and thanks Emmy again.